Hey guys, welcome to another tutorial on PyTorch. So today we'll just talk about gradient accumulation. So let's actually get started. Let's say we will import torch. Let's make a tensor is equal to x is equal to torch.tensor of, let's say, a value of 1. Okay. We will make sure that we require grad and we make this as true. Grad is to find a gradient. You can read more about gradients when you talk about slopes. Y is equal to mx plus c. So this is x is equal to torch.tensor with required gradients. Now what we'll do is we'll write a function. Okay. So y is equal to x square plus 2. Okay. So now what we can do is we can say y backward. Okay. And from this, so actually if we write y is equal to x squared plus 2, what do we expect the value of x to be? We expect the value, or sorry, what do we expect the value of y to be? Y is equal to 1 square plus 2, which is 3, right? What is the derivative of y? Dy by dx. We expect the derivative of y to be very simple. How much? That is 2x plus, it'll be 2x, 2 times x if you derive this. So that is 2 times 1, that is 2. So this is what we expect. So when I do y dot backward, then I can say print x dot grad, right? And what do I expect when I print x dot grad? I expect to get this dy by dx value, which is 2. So let's see, we're going to get 2, right? Give it a moment. I think it's booting up. Yeah, there you go. So you get 2. But now imagine if we update the value of y. Let's say we now make y is equal to x cubed plus 2. Then what is the expected value of y? Y is equal to, come on guys, that's 1 cube plus 2, that is again 3. But what is dy by dx? Dy by dx, it is equal to basically 3x square. 3x square. That is basically equal to 3 times 1, which is equal to 3. So it should be 3. So that's what we expected. But now if we do y dot backward, and one more thing, let's actually print y as well. So are we getting expected y? Let's see if we are getting expected y, right? You will not get the expected value. In fact, you'll get 5, and I'll tell you why. See, you got 5. Our expected value was 3, but we're getting it as 5. And if we look at y, are we getting the correct value for y? That is 1 cube plus 2, that is 3. That is correct. We are getting y is equal to x square plus 2. So that is 1 plus 2, that is 3. So are we getting the function 3, print y? Yes. Are we getting the gradient first? Correct. For the second one, when we are printing y, we are getting the correct value. Y is equal to 3. But we are not getting the correct tensor value. We are not getting the correct gradient value. That's because the gradient keeps getting accumulated. And that is precisely why we must zero the gradient first. And you have to be careful. You have to be careful. Otherwise, it will keep, adding up. Okay. So a very simple way to zero the gradient is you do x dot grad, okay, and then dot 0. That's all you do. And I'll show it to you. So now, ideally, if you're making a new function and everything else, we should ideally reset x. So we do x dot grad dot, let's check where is that 0? Yeah, dot 0. And what this basically does is it basically resets it to 0, right? So now, if I were to run it, now I will get the correct value, which is tensor is 3. So this is a very quick update on why you need to add the 0 grad function, okay? And there are other ways to call it as well. If I'm not wrong, there is one more way as well. So if I do x dot 0, what is it, the 0 grad? Actually, wait, PyTorch, documentation, 0 grad. Yeah. So this is optimizer 0 grad. So it's always a good idea to just read the documentation. 0 grad. Okay, so there are a lot of modules where you can actually set it to 0 grad. One of the ways is just to set a 0 with an underscore, as what I had done before. So instead of doing 0 grad, you can just do x.grad.0, and that should be fine. I think the other way to also do is you can do x.grad is equal to 0. I believe this will also work. if I'm not wrong, but I think this can cause small issues because of type errors. So yeah, it's got type as this, so you'll have to do 0.0 rather. And even then, assigning grad error to be a tensor. So if you do wait, torch dot tensor. I think this is the same. Yeah. So once you turn it into torch.tensor, again, it gets reset, or you can just write x.grad to 0. So remember, you have to set your gradients to 0 when you're doing these calculations. That's basically what I'm trying to say, right? And because these gradients will keep getting accumulated. And now we will also just go over why we need activation functions. Okay. So if you recall, we had basically got what do you call x, w1, w2, and you can actually create a collapsed x1, w1. That's basically what I want to convince you guys, right? And let's actually like give it a big example. Let's go ahead and give an example. So let's say we have a new gradient, okay, which is torch dot random. So x is equal to torch dot random of what? Of basically we're going to take the batch size to be wait why yeah, so we're reassigning x anyhow. So we're going to assign it as the batch size as 1 and number of inputs to be like 3. So that's what we're going to do. Okay, we're going to print x. I think we are redefining x. So maybe I'll call it as x1. Okay. Sure. Why do we have a bug over here? Unexpected indentation? Oh, my bad. Apologies. So stupid. I didn't realize that there is a space. Yeah, x torch random 1 comma 3. And now this is a random, this thing. Now let's go with two weights, W1 and W2, where W1 is equal to torch dot random of what exactly? Of so we're going to multiply x by w1. So the input needs to be 3, and maybe the output layer of w1 is 4. Similarly, torch.random 4 comma 2 or 4. Yeah. So so it's classifying. So this is the output, right? So you can print w1, w2. Now what we can do is we can say the hidden layer calc, right, is equal to x1 or rather x at w1. Okay. And then the output layer calculation is basically hidden at what? At W2. And we can say print of output, print the hidden print output, right? In this case, we are doing multiple calculations, right? We are doing two different layers in this neural network, right? So we got some output value. But the issue over here is this does the issue over here is that basically this thing is collapsible to just one weight without the non-linearity. If you recall, we had done a small section on what was the activation functions before. But if we really want to incorporate activation functions into this, I mean, like, why do we incorporate activation functions into this? Is because it adds non-linearity, which makes the neural network work. But without an activation function, this whole function, so we have done two calculations, right? Two, one by one. This whole calculation becomes a single collapsible calculation. That's what I mean to say. So this could also be written as, right? It could also be written as a matrix of 3 comma 2, which is W1 cross W2. So you could say here combined calc is equal to W1 at W2. Okay. And when you do combined calculation of W1 plus W2, you will again get the same output. So if you get here, output is equal to x at combined calc print output, you will get the exact same output, right? You're getting the exact same output. That means the whole calculation becomes a single function. But neural networks aren't a single function. They are multiple functions put step by step. And that is why they are able to do basically attach themselves to any curve. And that is precisely why we need activation functions. This was a corollary for you to understand why we need an activation function of sorts. And now to just clear it up a bit more for you, right? We can actually take the rectified linear unit or ReLU, if you remember. So we can actually take the ReLU output of this. For example, we have another another tensor. So if we write over here torch.tensor, okay. But here, what we're going to do is we're going to do something a bit special. We're going to actually rectify this, right? Torch.random, we will just put 3, okay, and then we'll just print x. Okay. So, oh, whoopsie. I mean, not torch.random. Yeah, so you got a random tensor of 3 variables, right? Of 3 different scenario of 3. But now I will write over here relu underscore output is equal to, what is output? Torch.relu, print relu output. Okay. And just have a look. So now it's 0, 0, 0 because all 3 were negative. So anything which is positive will remain, but anything that is negative will go to 0. That's what relu does. And you can see it adds this very weird form of non-linearity which can't be matched. So now, if we were to take our same previous example, right, and if we were to instead add, usually in between a hidden layer, you would basically multiply this, ideally, multiply this with a very simple ReLU layer. So if I were to do, right, for example, right, hidden ReLU is equal to torch.relu of hidden, and then I were to do hidden underscore relu at w2, then the output would be very different. And then again, I would say output underscore relu is equal to torch.relu of output, and then we would actually print the output relu, right? So in this case, this function is very different from doing the combined calculation and then doing output relu is equal to torch.relu, print output. So this is very different from that. So now you will get a different output. You will get different answers because of the non-linearity. This cannot be quashed into a single function. So for example, the final answer of the output relu was this, but with the 2 relus in between, this is the final output. So the outputs will significantly vary. That's what I mean by neural networks. Okay, maybe this sort of confused you, but basically you need non-linearities to create a neural network. And this was what I wanted to just prove to you in this small video. Hope you liked it. If you didn't, we will have to go over a bit of reading and theory. But in a nutshell, all it does is by applying ReLU, it makes sure that the outputs are not same. That's about it. Okay, thanks a lot.